Today we want to work with the ideas that we were working with yesterday. Remember, we're discussing functions of two variables. This is our first stop in describing things in three-dimensional space. And we're starting with the easiest one to work with, where one variable is a function of the other two variables. We know that the graph of the function of two variables will produce a two-dimensional surface in R3. That's what we're trying to get a handle on. And we're building this by thinking of the value of the function as the height above every point in the xy plane. The same way we build the graph of a function in R2 to make a one-dimensional curve. So with that in mind, I have some functions where I have sparse descriptions. So we have functions based on rates of change. And I want you to think about what the rates of change are and imagine how we would describe each of these functions. There are some things that we want to notice about what shows up in the equation and how that relates to what we see in the numbers. Math is about looking at patterns and describing the patterns that we see in the world and coming up with some kind of quantifiable system so we can make predictions and understand our world better. So here is a nice simple sliver of the world. We've got a numeric description of all these surfaces, and I want you to come up with functions for each of these four surfaces. Go ahead and pause the video now and try to come up with equations and think about what happens for each of these functions. All right, welcome back after that quick edit. So what about this first function? What are we going to write for f1 of xy? Secretly, it told me before, but I had forgot to start recording, so we're coming back to it. So I'm just going to take your answer from previous. I recognize that you're like, all objection, asked, and answered. So yeah, f1 of xy is just 7. No matter where we are on the xy plane, we're just going to get the value 7. Notice that the height does not seem to depend on x. It does not vary in the x direction. It does not vary in the y direction. The height above the xy plane is always 7. It doesn't matter about the x. It doesn't matter about the y. That's why x and y don't show up in our equation. No x and y, because x and y do not have an effect on the surface. X and y do not have an effect on the surface, so they don't appear in our function. So x, y do not appear in function. Since the height does not depend on xy. X doesn't matter, it's always the same no matter what x we pick. Y doesn't matter, it's always the same no matter what y we pick. When we go on to f2 of xy, it starts off with the same kind of thing. There's a 7 involved. But how does the value of the function change? What's happening? In the y direction, we're decreasing by how much? By 2, and how long does it take to decrease by 2? So y, the z value decreases by 2 whenever y increases by 3. So we can describe that as decrease by 2 every 3 units of y. So we've got a linear function in the y direction. This function looks linear in the y direction. When we picture this function, looking at it at a particular x value, we should just see a line starting off at 7 and decreasing by 2 every 3 units. What about in the x direction? How does x affect the height? It doesn't. So what are we going to put in for what the x does in our equation? Nothing. We're not going to have x show up in our equation. We're not going to have x show up in our function because x doesn't matter in this surface. The surface is the same for all the values of x. So x doesn't appear in our function. Because x doesn't change the value of the function. Now, before we move on to F3, I want to take a think about these two surfaces geometrically. What do they look like? Let's go back to F1. Geometrically, what is this graph going to look like? How would we describe that? It's not a line because we're in 3 dimensions. We're making a 2-dimensional surface. A what? A stair? Stairs go up, right? What's going up here? If we have the XY plane, everywhere above the plane is just 7. So thinking about F1, where the value is always 7. Everywhere above the plane, we have a height of 7. So I'm going to plot a point 7 feet above the ground. 7 feet because I can reach it. 7 meters is like upstairs and shit. So I can't reach it. 7 feet, I'm just going to have this point, then this point, then this point. Everywhere, I'm going to build a surface where the height is always 7. What's it going to look like? It'll be just like the ceiling. It'll just be flat. So I guess a stair would be fine because stairs are flat. You're just like, well, no. I was just thinking of one stair in particular. So yeah, this is going to be a flat surface. So this is just going to make a plane. A plane that's parallel to the XY plane, 7 units up. So this is going to be a plane parallel to the XY plane. Can everybody picture it? Everybody imagine it. I'll read your minds to check if you're imagining it. I'm just kidding. I'm not allowed to read minds anymore. You can't read people's minds. But it's so efficient to find out what they know. And I'm like, well, yeah, but it's in basics. Like, but they never know that I'm doing it unless I tell them. If I just don't tell them, they'll be fine. Okay? No. Eventually, we'll have a psychic student and they'll recognize. It happened once. I was sitting there reading people's minds, and the student was like, oh, wait, what? And I'm like, uh-oh, that student isn't here anymore, and you don't remember him. It was just yesterday, but you don't remember them. I've erased them from your minds. I'm just kidding. That didn't happen, at least in any way that you can prove. I'm just kidding. That hasn't happened yet. I'm just kidding. I'm not allowed to look into the future either. And yet apparently that's in my job spec. It's like, oh, you've got to prepare your students for their future jobs. I'm like, okay, so let me look into the future real quick and find out what jobs are going to be doing. They're like, oh, no, you don't get to look into the future. You just have to prepare them for a job that you don't know that they're going to be doing, that they don't even know that they're going to be doing, that might not even exist yet. Like a bunch of you are going to be doing jobs that don't even exist right now, but I have to so I got to train you for that job. So if that's the case, and I have to look into the future and shit, they're going to have to pay me a lot more than they do. Do you know what I mean? Meanwhile, they're asking this of the dude that's teaching the one subject in this entire school that has not changed in hundreds of years. And then when we get into the arithmetic part of the learning, hasn't changed in thousands of years. On one hand, I'm not qualified for the future stuff. On the other hand, maybe this is the only department that is. Anyway, what's going on with this surface here? what we've done is we've taken this plane, imagine this plane above our heads. No one here is over 7 feet tall, so it was safe to set the height at 7 feet. So at every point on the XY plane, I'm just putting a surface 7 feet above our heads. If the X direction is going this way, here's our X axis on this outer wall, and here's the Y axis on this wall with the board in it. What have we done for this second function? What have we done? What's the shape of the surface going to be? I don't know why I have to feel like I have to have my hands up here. For those of you at home, you can't see me, but I'm standing there with my hands up in the air, but like flat, as if I do care. Because I'm not waving them. So like, we got this flat surface in F1. F1 of xy equals 7. It's 7 everywhere. What have we done to this flat surface, this plane, in F2? Instead of 7 everywhere, it's 7 minus 2/3 y. So what do? I like that the first response was someone just holding their hands, kind of like doing this kind of thing with it. And that's exactly it, because it's exactly what I'm gonna do. We're just like tilting it in the y direction. You even tilted it in the y direction. Nice. You even remembered before I did which was the y, because this is the y. We're just tilting it in the y direction, but on the x direction, it's all the same. So it's a plane tilted down in the y direction. So it's no longer parallel to the xy plane. We just tilted it down, but only in the y direction. So it's going to be a plane tilted down in the y direction. We've got a plane tilted down in the y direction. Can everybody picture it? I'm a little plane, flat and wide. Here I'm tilting off to this side. That's all. All right, let's move on to F3. So in F3, I've still got this 7, 5, 3, 1, but then what's happening? What's now happening in F3? We're adding 4/5 of x. Now we're just going to follow the same pattern we did in the previous one. We can see that in the x direction, the values are going up. So we're taking the 7. We still have the minus 2/3 y, but now we're adding this 4/5 x. I guess I can't just not write them in alphabetical order. Kind of sad. Oh well. So if I plug in 0, 0, I get 7. 7 is like standing there. If I'm the constant value, I don't care about the x's and y's. This is what's happening when x and y are 0. X is increasing by 4, or z is increasing by 4 every time x increases by 5. So when I plug in x is 5 and y is 0, I've added 4 1 time, but subtracted 2 0 times. And that's what's happened with this 11. Then if we go down to the next line in y, where y is equal to 3, that means we have 7 minus 2 to take care of the y's, but we're still adding 4/5 x as x increases. What have we done to the shape of this surface? What's going on with the shape? Let's imagine the plane that we have in F1. It's all 7. I'm doing the hands thing again. And then in F2, we subtracted 2/3 y. So we tilted the plane down in the y direction. What are we doing in F3? We're just tilting it up in the x direction. So now like this, everything on top of this plane, all the dust on it is going to like roll down to that corner of the room. Because I've tilted down in the y direction and up in the x direction. So here's a plane tilted down in the y direction. And up in the x direction. Now we should check to make sure that this still works, because all I did was say, here's where we start, here's how we change in the y direction, here's how we change in the x direction. But if we plug in values, we can see that this works, mainly because we're working with such a simple thing. The y's and the x's are able to operate independently of each other. So, but if we put in, let's say 15, 6, when x is 15, we've added 4 3 times, because 15 divided by 5 is 3. So 7 plus 4 3 times. And we've subtracted 2 twice. 6 divided by 3 is 2. So we're going to subtract 2 2 times. And that's going to land us at 15. Just like we suspected. Any questions? What changes when I go to F4? What's the variant that we see in F4? Correct. In the x direction, we're no longer adding. What's our pattern in the x direction here? We're multiplying by 2 every 5 units in the x direction. So I've changed the rate of what kind of rate of change I'm using in the x direction. So that's the first thing to notice. So thinking about what exponential functions look like, in F1, F2, and F3, we've always had a plane. Started off with this plane horizontal plane, tilted it down in the y direction, tilted it up in the x direction. It starts off looking like, oh, we're going to tilt down in the y direction, but are we still even looking at a plane? You can tell by the tone of my voice that the answer is no. We're not looking at a plane anymore, because instead of just tilting and changing with a fixed value, now our rate of change is not going to be constant, because from 0 to 5, x goes from 7 to 14. That's an increase of 7. But then from 5 to 10, we have an increase of 14. So the rate of change is not constant in the x direction. So this is linear in the y direction, but nonlinear, and it's exponential in the x direction. So it's linear in the y direction. So it's not a plane, first of all, not a plane. It's linear in the y direction, but exponential in the x direction. So I have to turn my hands over, because I can tilt it this way, but it's going to be curled up in the x direction. It's going to be bent up in the x direction, because I'm building an exponential function as x increases. It's going to be bent up. Then the question becomes, can we just do the same thing? Can I just have a term for the y and a term for the x? So then that raises the question. Before, it seemed to work out, just have a term for the x change and a term for the y change. But we're dealing with very simple objects here, right? We're just dealing with so this is the question that we care about. Can we do the same thing that we did before? We've had this big change. We've gone from just changing with addition and all these flat planes, and now I have a change with multiplication. Things start getting bendy. So that raises the question, can we just do what we did before? Because the first thing that we should try when we encounter something new is just to try what we did before and see if it works. Then the important part is, when it doesn't work, to try something else. You know what I mean? Let's try. Go ahead. Question? Let's try it. Where do we want to start? What's happening at 0, 0? 7? What seems to be happening in the y direction? So it looks like we're going to do like a minus 2/3. But what happens? And what happens in the x direction? Oh wait, should I multiply everything? Just like do this times, and how do I multiply by 2 every 5 units? That'll multiply by 2 every 5 units. That gonna work? Could it be that simple? How can we find out? Plug some shit in, right? Perfect. Plug some shit in. See if this works. Try something and see if it works. By the way, this is all we ever really do as humans. We try something and see if it works. When it doesn't work, we try something else. And then when other people come along, it's like, well, hey, I've got this problem. It's like, well, you know what? I tried this and it didn't work. Then they'll be like, oh, well, what did work? So we haven't found that yet, but we know this doesn't work. Well, I'm going to try it anyway. All right. See, told you. See how it works? We just try it to see if it works. Notice we had some big decisions to make, right? What do we multiply by the 2? Do we multiply first and then subtract? What's going on here? Let's find out. What happens at 0, 0? Let's see. F4 of 0, 0. I got 7 minus 2/3 times 0 times 2 to the 0 over 5. This is a 0. 2 to the 0 is 1 times 7. So it works for 1. So we're good, right? It's funny because like this is clearly not good evidence that this worked at all, but we use this shit all the time because we're like, oh, hey, if I could do it, you could do it, right? So that's not how shit works at all. That's like you, if it worked for you, that's n equals 1. That's a terrible experiment. Let's plug in something else. Let's try it in, I don't, it doesn't matter which direction. You know it's going to work here. Let's try to get 14. So plug in x is 5 and y is 0. So I got 7 minus 2/3 times 0 times 2 to the 5 over 5. So we're multiplying by 2 one time, but we're starting with 7. 7 times 2 is, that seems to work. Moreover, we've established the pattern. When y is 0, this seems to work. When y is 0, we're just looking at 7 times 2 to the x over 5. And that's going to produce 7, 14, 28, 56 at 0, 5, 10, 15. So we're pretty sure this is working horizontally, at least for y equals 0. So what do we have to do now? Not y equals 0. Pick something else, right? So let's see. Because I like to overdo things, I'm going to go to 0, 3 and see if it lands on 5. See if we get these things work down here. So I have 7 minus 2/3 times 3 times 2 to the 0 over 5. So now the multiplication is not going to matter because we're multiplying by 1, and we're going to subtract 2 one time. So 7 minus 2 is 5. That seems to work. And what if we move to 5, 0? Let's see if that works. This is still F4. I spelled 4 wrong. Sorry, 5, 3. So we're going to start off with 7 minus 2 over 3 times 3, and then we're going to multiply by 2 to the 5 over 5. So 7 minus 2 one time is going to be 5, and then we're going to multiply by 2 to the 5 over 5. It seems to be working. The main thing that made it work was putting the parentheses around what we're multiplying. We're taking this first column and we're multiplying this first column by 2 every 5 units To multiply that entire column, we can't just multiply the changes by 2. We have to multiply the whole thing by 2. So the parentheses were key, recognizing that we were taking that first column and multiplying it by 2. So the answer here is no, I can't just have a term for the y and a term for the changes in x, because terms are separated by addition and subtraction, and the changes in x are changes through multiplication. So the answer is no. Terms are for plus and minus. X change is multiplication. So no, we can't just have a term for each one, but as long as we're careful with our parentheses, we can see where the y change shows up and the x change shows up. So a second. So the question says, is one way of determining what comes first that the change in y is not constant in the table? That was a little more tricky. We actually had a lot running in the background by deciding to multiply by the whole thing. If we had a constant y, then we wouldn't have the y term, and we would be so. If your question is one way to determine what's going on with how to multiply the x's by starting with a y term, that would be a good way to simplify the problem. What if we didn't care about the y? What if it was 7 all the way down? Making this 7 all the way down would take out that first column is changing. So I have to multiply the 2 times to the x over 5 by whatever's in this first column, and then put the changes in that first column inside there. Any questions? Is this a comprehensive look on how to build surfaces from a snippet of a table of values? Totally not. We've only looked at like 2 different kinds of chain. There's a much more to the story of describing stuff. But in the 3 things that we do in calculus, the biggest one is always describe stuff. We spend a lot of time like derivatives and integrals because you have derivative rules and then all the weird integral rules. But really what we're spending most of our time doing is describing stuff. Question? So as far as the order of tracking your changes goes, identify what changes you want to have there, and then just experiment. Does that make sense? Because that's all we did here. We just happened to get lucky because I just multiplied this whole thing. But the important thing is to note what things you want to, what are the changes that you want to track? How are we going to track them? Through addition and subtraction or through multiplication? And then notice how we could change certain things. How are those changes going to affect the values in the outcome? So not really. We just have to, the way to proceed is to know what we're trying to say, know how to say that, and then we can take those things and put them together into a sentence. Yes. Division is just multiplication. So if this was cutting in half going this way, it'd just be times 0.5 to the x over 5. All right, that's going to do it for today. If you didn't sign in on the sign-in sheet, you're here in the classroom, please sign in on your way out. I'll keep right up here. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.